All right. Welcome, everyone. Thanks for joining us here on a Friday afternoon here, November 3rd, 2023. I'm Kerry King. I'm Assistant Director and Research Scientist at the Energy Institute at the University of Texas at Austin. It's my pleasure to introduce kind of a special edition of our Energy Symposium speaker series with two of our very own faculty and scientists here, talking about creating the global markets for low greenhouse gas emissions natural gas. To let you know who we are speaking with here a little bit more, David Allen is the Norbert Dittrich-Welch Chair Professor in McKetta Department of Chemical Engineering. He's also the head of the Center for Energy and Environmental Resources Unit here at the University of Texas. He's also the winner of the ENI Energy Transitions Award, which has been referred to as the Nobel Prize for Energy, and he's on the National Academy of Engineering. Joining him is his co-director of the Energy Emissions Modeling and Data Lab, which is what we're going to hear about today, Arvind Ravikumar. He's the co-director, and he's a research associate professor in the Hildebrand Department of Petroleum and Geosystems Engineering. So today we're going to hear about the work on understanding the emissions of the supply chain of natural gas. And without further ado, I'm going to hand it over to Dr. Allen and Ravikumar.
Thank you, Kerry.
Thank you. All right. I'll switch over the presentation for you. We might mention one thing before they get started. Please submit questions via the question and answer feature of Zoom. For those of you in the room, you don't have to do that. You can ask them directly. And we will take the questions at the end of the presentation. So thank you.
All right, great. Thank you. And thanks for those of you who are in the room for being here on a Friday afternoon. Arvind and I are going to talk about creating global markets for low greenhouse gas emission natural gas. I'm going to set the stage and describe what parts of this problem we're looking at. And then Arvind will specifically talk about what we refer to as ENDL, the Energy Emissions Modeling and Data Lab at the University of Texas. So let's go ahead and begin. I'm going to try, okay. So I think probably everyone online and everyone in the room knows that energy production from the United States is increasing, both oil and natural gas. These are Energy Information Administration projections of production and consumption. The United States is becoming the global leader in natural gas production and is a leading supplier of natural gas to the world, both through pipeline to Mexico primarily, but also notably through LNG, now distributed around the world, and potentially becoming one of the largest exporters, if not the largest exporter of liquefied natural gas. This not only is an important component of the global energy picture, it's also strategic for global energy security. Nothing reflects that more than what happened with the Ukraine war. As Russia invaded Ukraine and Europe shifted away from Russian gas, what happened was the United States, as you see on these dots, going across the figure, dramatically increased its exports of natural gas to the European Union, largest natural gas importing region in the world. And so not only is it important economically and for the global energy sector, it's also critical for global energy security for the US and its allies. But is increased global use of natural gas compatible with climate goals? And that's really what we're going to be addressing here. And so at first pass, it's clearly advantageous for our climate goals. If you look at the US emissions of greenhouse gases is kept track of by the US Environmental Protection Agency, as you see on the right. What you see is on the right plots of generation of electricity, and then as the black line, emissions of carbon dioxide from electricity generation in the United States. And it has gone down dramatically as the US has shifted away from coal, which is that central tan region, and as natural gas has increased and renewables have increased, but notably as natural gas has increased. So switching from coal, which has an average emission of a ton of CO2 per megawatt hour generation, to natural gas lowers CO2 emissions from combustion by more than 50%. And that has driven CO2 emissions from electricity generation substantially lower, but also the entire US inventory of emissions of greenhouse gases has been driven to lower levels by that decrease. So for CO2, the question, the answer to the question of is switching to natural gas beneficial for climate is pretty clear. We get a dramatic reduction in CO2 emissions switching away from coal. However, power plant emissions aren't the whole story. We also need to be concerned about leakage of methane. Methane is a greenhouse gas. And if we get emissions of methane from the wellhead to the burner tip, that may mitigate some of the CO2 advantages of switching from coal to natural gas. Coal has its own methane emissions, but they tend to be smaller than the methane emissions associated with natural gas supply chains. So methane emissions are a big issue. And methane is a substantial part of the overall warming of the atmosphere since the Industrial Revolution. These are data from the Intergovernmental Panel on Climate Change, which show the warming on the left, the warming in the atmosphere due to various greenhouse gases since the start of the Industrial Revolution. So take the change in the atmosphere since the start of the Industrial Revolution, say, calculate how much warming is due to those changes, and you see that methane is on the order of 25–30% of the total amount of warming due to the change in the composition of the atmosphere. And on a kilogram for kilogram basis, methane in the atmosphere is 120 times as potent as CO2. Now, those of you who follow this issue closely will say, 120? That doesn't sound right. I hear numbers like 84 or 32 times as potent. Potent is methane. Well, the science is pretty clear. Science is not ambiguous. But what we need to recognize with methane is that it's referred to as a short-lived climate force. In other words, it will react in the atmosphere with this OH species that you see on the right, and will eventually form carbon dioxide. Half-life for this reaction in the atmosphere is about a decade. So if you emit a molecule of methane today, over the course of about a decade, half of it will disappear and eventually form CO2 in the atmosphere. And so as we think about how much warming is caused by methane, we can compare the warming caused today by a kilogram of methane, and that's equivalent to 120 kilograms of CO2 today. Emitted today, compared today, 120 times as potent. On the other hand, if you average over 20 years the effect and calculate the warming over 20 years, it's 84 times as potent. If you calculate the warming over a 100-year period, it's 28 to 32 times as potent. So how potent? It's not that the science is ambiguous. It's the time horizon that we're interested in. But nevertheless, methane is a potent greenhouse gas. I will tend to refer to this 20-year time horizon. And if you listen to later this month as the climate negotiations begin in the UAE, if you listen to their discussions of methane, the number that you will hear most frequently is 84 to 86 times as potent. Okay, so a potent greenhouse gas if methane emissions from the energy sector were a country, it would be the third most emitting country in the world, behind the US and China. So 135 million metric tons of methane emitted annually from the global energy sector. And here, this is using roughly a 25 times potency to get this number. Use the 84 or the 120 and get a different value. But all told, from the energy sector, methane emissions are a big contributor. Are they the only contributor? No. Let's look at an overall balance of methane going into the atmosphere. How much methane is there? And let me point out to you on this overall global methane budget, what we know precisely and what we know less precisely. So what we tend to know precisely is a global average methane concentration, about 1.8 parts per million in the atmosphere on a global basis. We know about the only way it disappears from the atmosphere is this route, reacting with that hydroxyl radical that I showed you earlier. And we know that reaction rate really precisely. We can calculate this number with a fair degree of precision. So we know the loss rate. We also know the rate at which methane is accumulating in the atmosphere. So we know the amount leaving the atmosphere pretty precisely. We know the amount that's increasing in the atmosphere pretty precisely. And so we know total emissions globally pretty precisely. What's less certain is what the different contributors are. A lot more uncertainty there. But nevertheless, about 60% of the stuff going into the atmosphere is from human activities. And about 40% is natural, wetlands, termites, other sources of methane. So of that 60% that is man-made, on the order of 100 teragrams, 100 million tons a year, globally from the oil and gas sector, about 100 million tons. About almost 200 million tons from the combination of agriculture and waste. So think ruminant animals like cows, think their manure, think rice agriculture, and a few other major sources constitute the agricultural sources. Again, almost 200 teragrams a year. And that's largely the human emissions. It's believed that the emissions that can be reduced most rapidly are here. That changing people's diets, changing rice agriculture around the world will be a relatively slow process compared to trying to reduce methane from energy sector sources. And if we take that 100 million metric tons a year methane emissions from the global energy sector and use that potency of 84 times as much, that's the warming equivalent of taking all the cars in the world off the road. Take the CO2 emissions, tailpipe emissions, take them to zero. That's the warming equivalent of getting rid of 100 teragrams a year of methane from the energy sector. A big target that can be achieved in the short term. So what do we know about these emissions? People like me have spent the last decade making measurements of all sorts from the global energy supply chains, but principally here in the United States. We've gone directly on sources. We've put monitoring stations out in oil and gas production regions. We've driven vehicles downwind and looked at plumes. We've flown airplanes. We've looked at satellite data. We've taken all that information. I'm not going to take you through that, but let me give you the headlines. What have we learned? after a decade of measurements. So particularly in the United States, where almost all the measurements have happened, on a global basis, but as well in the United States, from wellhead to burner tip, about 2% of the methane that comes out of the ground gets into the atmosphere before it reaches the burner tip. And so 2% of methane produced. If we take that potency of 84, that erodes about 2/3 of the CO2 benefit that we get by switching from coal to natural gas and electricity generation. So it's a significant part of the overall picture of what the warming potential is, the greenhouse gas emissions are from natural gas systems. Second thing we've learned is that averages don't tell the whole story. There's substantial variation from site to site, from basin to basin. So for example, go to the Haynesville, and the fraction of the methane that's getting out in the Haynesville is around 0.1%. In the Permian, there are a bunch of different numbers that are out there in the scientific literature, but let's just say broadly around 4%. Typically, the lowest numbers that are out there in the scientific literature are around 3%. They go much higher than that, but still substantial variation from basin to basin and country to country. Even within a basin, detailed analyses up in the Barnett Shale in north central Texas indicate that 2% of the sites in the Barnett give us about half of the methane emissions. And those are not the biggest sites. They're the high emitting sites, but they're not necessarily the biggest sites. You want to think about this. It's not surprising to someone who's studied air quality for a long time, like I have. Let me give you something that will make it familiar for you. All right, so this is now being called these 2% of sites in the Barnett Shale under a new program from the Environmental Protection Agency. These are being called super emitters. Okay. We've had super emitters forever in the air quality. We've known for decades that 10% of the cars on the road give us 50% of the emissions from cars on the road. And you've all driven behind them, right? And why are they emitting so much? Well, maybe something's broken, or it's old equipment, or something else. So super emitters are not a new phenomenon, but we have them in natural gas supply chains. So we can go out and measure these emissions, but many of them are intermittent. They may be hard to detect. They may or may not reoccur if they've occurred once at a location. So all of this information has led to global, national, and other goal setting for reducing methane emissions at multiple scales. So beginning with the climate negotiations that happened about 2 years ago, multiple countries representing about 45% of global methane emissions, pledged to reduce their emissions 30% by 2030, including the United States. So global pledges. There are also state actions that are occurring. If you follow this space, Colorado has some of the leading regulations in the world in terms of what they're trying to do on methane emissions. There are regulations in California, in other states. So at the state level in the United States, there are regulatory actions. There are industry actions, both through trade groups and other organizations, where in this case, through the OGCI, the Oil and Gas Climate Initiative, commitments are being made to try to go to near zero by 2030. So a number of major oil and gas producers have signed on to this commitment to try and get to near zero methane emissions by 2030. we need not only to think about methane emissions in fixed locations, if we're going to think about markets for low emission gas, we need to think about supply chains. So thinking about all the emissions along a complex supply chain that might look like this. And there are consortia of companies like One Future that represent organizations all along the supply chain that are collectively committing to try and reduce emissions by substantial amounts. So we've got global goals, national goals, state goals, supply chain goals. You're going to have goals. You have to measure against these goals. And so a decade ago, when we first started making these measurements, these are measurements from a UT-led campaign, making some of the first measurements of methane emissions from oil and gas facilities in the United States back in 2012, so over a decade ago. And this is what we were doing. We were going directly on the emission sources, making measurements. It was expensive. It was really time consuming. We learned a lot, but we've now transitioned to having multiple scales of measurements. We have a whole portfolio of measurements available to us now. The space on methane emission measurements has just exploded, particularly over the last 5 or 6 years. It's at a variety of different spatial scales, and the measurements themselves are made at multiple temporal scales, ranging from very short duration measurements to much longer time series of measurements. So we have various types of aircraft measurements. We have fixed ground measurements. We have on-site imagery. We have satellites. There's a rich portfolio of measurements. So let's take a closer look for a moment at what we're actually trying to measure, because the signal is complicated. So let me try and explain to you 3 different spatial scales what the signal looks like for oil and gas emissions. So let's start at a relatively simple well site. So let's start at a relatively simple well site. We'll zero in on the Midland Basin. So let's go into the Midland Basin. We're going to show cartoons and synthetic emissions, but they represent the sorts of things that you would get for methane emissions on some of the 500,000 gas producing sites in the United States. So on a site, and this one's intended to reflect producing both hydrocarbon liquids and gas, we have the wellhead. Wellhead feeds this separator. Separator is controlled by pneumatic controllers that periodically discharge liquids. When they discharge liquids, they vent. The pneumatic controllers vent. That's how they're powered. These sites are often not able to have electrical power. That discharges high pressure liquid containing methane into these atmospheric pressure tanks. Some of them may vent, like this tank. Others may have control technologies on them, like a vapor recovery unit, as illustrated here. But that will give you periodic emissions. You might have a pump that's being operated using the pressure of the gases produced at the site, a pneumatic pump. That's shown here for chemical injection. All those are planned emissions. And then you could have leaks that appear like that. So if you're making a measurement at the site, you're going to see all this signal, right? And that's what each individual signal is going to look like. And if you add them all together, if you have something downwind that's making a measurement of the site, you'd see something like that. And now what you really want to do is deconvolute that and understand where the sources are and what you could do about individual sources. So you need to attribute those emissions to the individual sources on the site. And if you look at any individual time, you'll see a different distribution. Is the tank venting when you look? Is the pneumatic controller going off when you look? Is Has the leak occurred when you look? Right? All those will give you different components of the signal. So the signal at an individual site is going to be complex and is going to have intermittency in it. What does the signal look like at a basin scale? So a number of years ago, we did together with many others, did analyses of the Barnett Shale in north central Texas. And so now if you flew back out and could say, I'm going to look down on the Barnett Shale and look at emissions hour by hour at individual sites in the Barnett Shale, what would you see? What would that signal look like? Okay, so let's look at that. Here's the counties in which the Barnett Shale is located in north central Texas. This is what you would see, all right? And lights are on in the room, but those of you online are undoubtedly seeing that you get these large short duration pulses that constitute about half of the emissions in this area, and then lots of other low level emissions at the 20,000 or so sites in the Barnett Shale. And those constitute about half of the emissions. So you've got this regional variability. So if you're going to fly over with an airplane or fly over with a satellite, you're going to see a snapshot of this. How are you going to interpret that? Not an easy problem. On about an even broader scale, if we took some of the biggest emissions that have been observed out in the Permian Basin, and then asked, all right, how is that going to distribute over much larger scales? This is what it would look like. And so we can get influences of methane releases over very large spatial scales. So the signal that we're trying to analyze is complicated, and is complicated at many scales and at many time scales as well, many spatial and temporal time scales. So we've got great tools now, and we've got a really complicated signal. How do we make progress? We need to take all this information, combine it all, and from that, get an idea of what the emissions are from supply chains. And given that problem, we've been working on that problem for a decade now. We pulled together a team to form this new energy emissions modeling and data lab. I'm going to let my colleague Arvind Ravikumar talk specifically about what we're doing now to try and combine all this information and particularly apply it to global markets in LNG. So Arvind, all yours.
All right. Thanks, Dave, and thank you all for coming here, both for those in the room as well as those who are online. What I'm going to be doing over the next 20 minutes is give you a couple of examples of what we have been doing over the past year since we launched EMDL. So we launched EMDL early 2023 around January. It's a collaboration between 3 universities, UT Austin, Colorado State University, and the Colorado School of Mines. And we've been working on synthesizing all of the information that's been available to us on methane emissions from oil and gas supply chains, and thinking about what does it all tell us in the context of global markets for LNG and natural gas. All right, so what do we do as EMDL? So our mission is to provide timely, reliable, science-based, transparent, and measurement-informed greenhouse gas emissions information on oil and gas supply chains. And one of the products that we're going to get out of doing this work are sort of 4 key things. The first one is organizing and convening. And I'm going to give you an example of how we do that. But as you saw before, there's a lot of activity happening in the methane space. There are measurements that are conducted by universities, by non-governmental organizations, by regulatory agencies, by oil and gas operators. And then there are policy developments that happen not just in the US, but around the world. And now we have international climate negotiations happening on addressing methane emissions from oil and gas operations. We have the Global Methane Pledge, which was signed by over 150 countries to reduce methane emissions by 30% by 2030. And so the question is, with so much of activity happening in this space, how do we make sense of all of the information that's coming in? So one of the key things that we're doing in the methane space as experts in the field who've been working on this for a while is to bring people together find out where are the key gaps in our understanding of emissions and its use in public policy, and then try and develop solutions collectively as a community. So that function of organizing and convening people and experts on the space is something that we've started doing as we launched eemdl as a key part of what we'll do going forward. And I'll give one example of how we are doing that. Then, of course, we have the key scientific output, which is models, tools, and methods. You saw the different types of methane emissions information we're going to get across our supply chain, from satellites, from aerial systems, from drones, from the operations, etc. How do you interpret all of that information? How do you interpret that information in a context that's useful for public policy? What's a public policy? Something like a carbon border adjustment tax. So if you're going to tax products and goods on carbon emissions embedded in those, how do you measure them? And so what we're developing are models and tools to help interpret all of the data that's coming in space. And then we publish those data sets. Right now, we are doing a lot of work on measuring emissions in the United States, but that's going to expand very soon across global regions because satellites are expanding in their capabilities very quickly. So we are developing data sets to provide the most up-to-date information on greenhouse gas emissions. And then the last thing is training and education. As much work as we do here at UT, as many students as we have on these projects, the scope of the problem is much, much bigger than any one university or one initiative. And so a key part of what we're doing is to be able to train people around the world on how do you use these models, how do you use these data sets, so that they can take those models we're developing and use it in their own context. So we have regular training sessions and webinars or workshops to make sure that stakeholders in this space, so that's whether it's an oil and gas operator, whether it's the EPA or other regulatory agency, or other scientists who want to learn and use these tools. So we train them to make sure that the tools and the models we develop are used widespread around the world for addressing the methane challenge. All right, so why do we need accurate greenhouse gas emissions information? So what you're seeing in this chart are sort of what happened around the world just in the past 2 years. What you're seeing on the x-axis is sort of scale, spatial scale. You start from the smallest one on the left, which is asset or a facility, which can be anywhere between a few hundred feet across. And then you have individual operators, you have regions, and then you have basins like the Permian Basin in Texas and New Mexico. And then you have national level scales. So country level emissions. Until recently, until about 2-3 years ago, all we needed was national level emissions estimates, similar to what the EPA has been doing for the past 30 years, the greenhouse gas inventory, GHGI. They've been developing this for all sources that emit greenhouse gases, and they've been compiling this at the national level. But what has happened in the past few years are a whole host of new policies and paradigms that require much more detailed information. National level data are not enough anymore. You're going to need information at much higher spatial resolution. And some examples of what those newer policies are up on the board. So you have something called as differentiated natural gas, where companies are trying to price emissions into the cost of natural gas. So if you have lower emissions, you get preferential access to markets, you pay a premium for low emissions natural gas. The European Union is thinking about a methane import standard where the price of natural gas is tied to the emissions embedded in that natural gas. We have investors and the insurance community demanding that the companies they invest in reduce the footprint of their greenhouse gases, including methane emissions. And then you have the methane fees in the Inflation Reduction Act, which is a fee that's assessed at the facility level and at the operator level. So for all of these kinds of policies to be successful, you're going to need emissions information at much higher spatial resolution. You're going to need emissions information that's accurate at the asset level, at the operator level, at the regional level, etc. And so what has happened because of this is policy developments in how do you do this? How do you get information at such high spatial resolution, not just in the US, but around the world? And so the Department of Energy in the US is currently participating in a 15+ country international working group to develop a shared framework for measurement, monitoring, reporting, and verification. It's called MMRV, and you're going to hear this over the next 5, 10, 15, 20 years a lot. And you're not going to hear this just on methane. You will hear this in hydrogen, you will hear this in carbon capture, and you will hear this in carbon removal. The idea is, if you say you're going to reduce emissions by something, how do you know you've done that? How do you accurately verify you've reduced emissions by a certain amount, or your emissions intensity is a certain number? So you have to do measurements, monitoring, reporting, and verification. And so the DOE is working with major LNG exporting and importing countries around the world to develop a shared framework for this, so that the measurements that we do in the US can be compared to measurements that are done in Algeria. That can be compared to measurements in Qatar. That can be compared to measurements in Malaysia. How do we develop a shared framework? So everyone does their own measurements, but can compare the data and then go about reducing emissions from individual global natural gas supply chains. And so the goal of all of this is to enable credible verification of greenhouse gases across these supply chains. So what did we do? So as observers and participants in this kind of work, as someone who are doing these measurements, we wanted to bring together and talk to experts and find out if this is going to work at a global stage. In fact, we might even see announcements at COP next month based on some of the work that the DOE has been doing. But the question is, if this is going to be successful, what do we need to do? Where are all the technical gaps to be able to enable something like this, a global market for low emissions natural gas? And so we worked with CSIS, Center for Strategic and International Studies. It's a think tank in Washington, DC. We organized a workshop this past summer that brought together experts on this topic from various organizations to think about the technical issues that you need to solve to develop a differentiated gas market. And so this was a meeting where we identified 5 key building blocks that are necessary. We didn't solve anything, but we identified, okay, these are the 5 things you need to do, you need to solve before you can make a global differentiated gas market work. And so this paper just came out yesterday. So we made the slides last week. So it says that it'll come out in the next 1 to 2 weeks, but the paper came out yesterday. It's available online. But the idea was this. We developed a framework for where are all the gaps in developing a global market for low emissions gas. And so we talked about sort of 5 different things. The first one is, of course, the measurement-based emissions estimates, which you've heard over the past 30 minutes. And then you need models that are transparent. So you don't want someone to interpret emissions data that happens in a black box. You want everyone to know how it's interpreted. You want data quality metrics. So you want to know if the quality of data that's coming from the United States is as good or as worse as data coming from other parts of the world. And so how can we improve the quality of data over time across different countries and different operators? And then we need reporting frameworks. Okay, every country, every operator does these measurements. At some point, they'll have to make that public. They'll have to report it to someone. So what kind of reporting frameworks you're going to have? So it's all comparable across nations. And then the last thing is independent verification. At the end of the day, you've got to be able to verify what these emissions are. If someone claims that they've done the measurements, they've done the models, they are reporting their emissions as very low emissions, you have to know that they're telling the truth. So you have to have some way of independent verification. Now, we don't yet know what that independent verification looks like, but that's going to be a key component to build trust in these differentiated gas markets. All right. And it's not only that we need these technical solutions, you need these solutions to be accompanied by training and capacity building. As Dave said earlier, almost 90% of the measurements that we've seen in oil and gas methane emissions have happened in the United States. We know a lot more about it than most other places in the world. So they can't just turn on the clock tomorrow and start doing all of this at a very high level. So you're going to have training and capacity building across operators, countries, and organizations. And that's because they're all in different places when it comes to deploying new technologies. In fact, there are about, I would say, 50 to 80 startups that do methane emissions detection and quantification in the United States or around the world. 90% of them are startups in the United States. They've all been started as companies here. They've been doing a lot of their measurements here in the US. None of, or very few of these technologies have actually done measurements internationally. So how do you think about technology deployment in other parts of the world? It's an important question when it comes to having a global differentiated gas market. All right, so what we are doing is, as part of our convening activity, we launched a differentiated gas road mapping initiative to convene experts to identify the technical, to solve some of the technical questions we have. So as we said, we just identified the 5 key building blocks for enabling differentiated gas markets. And now we launched this initiative with a group of about 30 to 50 people from around the world to start chipping away at some of these technical questions. And so the goal is to establish a coordinated effort that brings scientific policy and market gaps for practical and scalable adoption of differentiated gas. And so this activity is going to happen over the next year, so that by the end of 2024, we'll come up with some solutions for some of the key building blocks and technical gaps that we've identified. And the idea, as I said before, is to not do it in silos, but to bring the community together. So there's not one solution from Texas, one from Colorado, and one from Qatar, and one from Japan. We want solutions that are broadly applicable, that everyone agrees on. And part of convening is to bring people together and make sure that we develop solutions that are broadly acceptable to people. And that's an activity that's going to be happening over the next year. So this is one example of how we are using our convening authority to be able to move forward some of the solutions that are necessary to take this to the next level. All right, so what are we actually going to do as part of this initiative? We'll develop review papers, state-level science review papers. We'll have commentaries and white papers that inform international negotiations on building this differentiated gas framework. And then we'll have methods and technical guidance that could be adopted by various regulatory agencies around the world. In fact, we want this to be a broadly engaged process with all stakeholders. So everything that we put out will have a 30-day comment period. All the papers that describe these technical solutions, the methods, and the guidance will be available for public comment. We'll also, of course, work with key stakeholders to gather their input into this process. And we'll be holding virtual workshops so that people who are not part of the team that's developing this can also provide their input into what these technical methods and guidance are. All right, so I talked about organizing and convening and an example of how we are doing this. The next thing I want to talk about is one example of the technical work that we are doing right here in the United States. And that's going to be talking about measurements across supply chains. So one of the things that we have seen so far is that there are a lot of different technologies available for measurements. Satellites, aerial systems, drones, and on-ground sensors. In parallel, there's a need for differentiated natural gas, so highly resolved emissions information, not just at the national level, but across individual supply chains, individual assets, and individual operators. So what we did was we partnered with ENI Energy to measure emissions across individual supply chains. So what you're seeing here on this graph are some of the major basins from the country. We took 3 basins as our pilot project. So the Marcellus Basin in Appalachia and Pennsylvania, the Permian Basin in West Texas, and the Haynesville Basin in Texas and Louisiana. So we measured methane emissions for individual supply chains. So we went to the production facilities. We traced the methane emissions to individual pipelines. We measured emissions throughout the pipelines, all the way until it ended up at a liquefaction terminal on the Gulf Coast. The goal was to not just estimate emissions for natural gas supply chains in the United States, but to directly measure emissions across a specific supply chain. So we considered 2 supply chains: gas that comes from the Marcellus Basin and goes to the Gulf Coast, and the gas that comes from the Permian Basin and goes to the Gulf Coast. So we used multiple scales of measurements. As we saw before, different technologies give us very different kinds of information. So here's an example, right? There are 4 levels of measurements. Level 0 is things that's literally on the ground, you put on the facility, called continuous monitoring systems. This is much like a smoke alarm on this room. If it detects a methane emission, it'll throw out an alarm. Hopefully someone will come out and fix it. But the advantage of those kinds of technologies is that it'll flag if something is wrong in your facility, and it'll send a flag to an operator who can come out and fix it. So it's sort of an alarm system. And the next level are drones, which fly anywhere between 10 and 50 feet off the ground. And the idea of these drone surveys is that it can tell you for individual equipment on the site what's happening and what kind of emissions are we having on those equipment. And then level two. Level two is aerial systems, which fly anywhere between 1,000 to 3,000 feet above ground. The advantage of aerial systems is that they're fast. They can cover hundreds of facilities in a day. And so you're going to cover a very large area to get your emissions information. And the last thing is satellites. Satellites might not give you information on individual assets, but they're great at monitoring over time. So if you want to know because of certain regulations or certain company practices, how has your emissions changed over the course of 12 months, 18 months, 24 months, satellites are great to be able to help you monitor those things. So what we did was, we did these measurements over a period of 12 months. So we did an initial baseline monitoring, which means that we didn't know what the emissions were, so we had to go first find out. And then we monitored the facilities for a period of about 6 months. And then at the end of the period of monitoring, we came back and did some verification measurements as well. And the idea of this is to do it across the supply chain. So you did on the upstream, it was a collaboration with 5 different producers in the US in the 3 basins. Then we have midstream. So every gas that comes from these production facilities has to find its way through pipelines to liquefaction terminals. So we partnered with about 7 or 8 different midstream companies to go and measure their facilities. And then, of course, we have liquefaction terminals where we measure emissions, and then finally shipping. So we went to, our collaborators went on a ship to measure methane emissions on board. And the idea is to develop supply chain specific methane emissions estimates. So every cargo that goes out of the terminal at Sabine Pass in Louisiana will have an emissions tag associated with it. And that tag will tell you what is the emissions intensity of the natural gas that's on that ship. And that's based on all of these measurements across the supply chain. And so what we found was that it's not that there's only one solution, one magic solution that you can use everywhere. It's that multi-scale measurements are complementary. You want to use continuous monitoring sensor in conjunction with aerial surveys because they give you different kinds of information you're going to need. And you're going to need all that information to do something like this, to develop cargo emission stats. So at the end of the day, what are you going to do with all this information? In this example, what we're doing is developing emission stats. So what Shania will do is they take all of the measurement data that's been collected in the upstream, the midstream, the liquefaction terminal to talk about what is the emissions intensity of an individual cargo of LNG. And this was just a pilot project. We wanted to try to see if we can measure emissions across the supply chain. But this is an example of a project that we're doing. So right now, we have campaigns ongoing in the Marcellus Basin in Pennsylvania, in the Permian Basin, and in the Denver-Julesburg Basin in Colorado. All trying to understand how do we better get accurate estimates of methane emissions from oil and gas supply chains at a much higher resolution than what we have had so far. And so let's say we do all of this and we solve the problem and we found ways to accurately estimate methane emissions. We're able to get methane emissions at very high resolution. What would we have learned if we achieved our goals by 2030? And this is something that's very exciting to me personally, because this is the first time in the world that we're trying a very complicated measurement, reporting, and verification system for a globally traded commodity. We are doing all these measurements in the US. We know how difficult and how challenging it is, but to be able to get this to work at a global level, we have to do these kinds of measurements in very different environments, in the marshy swamps of Nigeria, in the dry deserts of the Middle East, and in Asia. So we have to do it all over the world. But if we do it successfully, then we'll have a robust system for MRV that is globally valid and that helps us to know exactly what our emissions are along natural gas supply chains. And the key part of this is, as I started by saying this kind of MRV work is important not just for natural gas. It's going to inform everything that's going to come in the future when carbon emissions are lower and every molecule of carbon that's emitted becomes that much more important to count. And so that's going to be hydrogen next. We just had the announcement of a hydrogen hub, of which UT is a partner. That's going to happen in carbon capture. You have to make sure that you're capturing the amount of carbon you say you're capturing, and then it's going to happen in carbon removal. And so the hope is that if we're successful getting a global MRV system in place for natural gas that people trust, that people use. We can take some of those lessons and insights and translate it to some of the newer technologies that we're going to need that are coming up quickly, like hydrogen, geothermal, carbon capture, and direct carbon removal. And that's our goal. We want to get this done for methane in the next 5 to 10 years, and then think about what this means for some of the other energy technologies that we're going to be needing in the next few decades. With that, I want to thank everyone for being here and see if there are questions.
Okay, thank you very much. There are a few online. We can start in the room if anybody has one. Otherwise, I'm going to go online. All right. Got a question online here. So maybe this one sort of to the end is sort of where you ended up a little bit, Arvind. The question is the monitoring and recording and verification of data of the supply chain, using the term evidentiary grade, if this means something to you, I don't know, with calibration and traceable integrity from source to repository. So is it the intent to provide the technical methods and data suitable for government, statutory, and regulatory enforcement? Is this what you mean by the tags that would be associated with the shipment of LNG, or is it something slightly different?
Right. That's a great question. It's also a very complicated question because there are different levels of accuracy needed for different applications. So one of the things that's at a more advanced stage right now is thinking about how will all these measurements translate to regulatory reporting. For example, every operator above a certain level has to report to the EPA what their emissions are. They're doing all of these measurements. So how do you take all those measurements and do it through the formal EPA reporting process, the greenhouse gas reporting program? That's a place where you're doing a lot of research on. We're figuring out what's the best approaches to make it consistent across operators and regions and seasons. And then there's the next level. How do you do this at the global scale? There are new initiatives such as the Global Oil and Gas Methane Partnership, or OGMP 2.0, that is developing a reporting framework for methane emissions around the world. There are about, I think, 50 or 60 companies that have signed up for that. Essentially, signing up to this means that it's a program managed by the United Nations Environment Program to bring some consistency to reporting. So if a company signs up for it, every company that submits to that has a consistent reporting format. And then there's the third level, which is for sort of the investor community, and then making this some of the ones that refer to the questions. That's where we are at a very early stage. We are still have to figure out what the methods are. How do you make sure it's trusted? How do you make sure that it's transferable and you can sell credits based on emissions? That's something a lot of companies have started up, but something we are still figuring out what's the best approach to do it. Dave?
Yeah, maybe let me add a different dimension to that question. And first, point to the urgency of addressing it. What is suitable as evidence? And what makes that particularly urgent here in the United States is a combination of three things, all of which are either proposed EPA regulations or the Inflation Reduction Act. So let's first look at the Inflation Reduction Act, which imposes a methane fee above a threshold. I won't dive into the details, but above a threshold, you pay $1 a kilogram for every kilogram of methane that you emit. $1 a kilogram. If our number is right for the 2% of the methane that's leaving the ground, getting into the atmosphere in the United States before you hit the burner tip, how many dollars is that? $15 billion a year? Right. Who gets the bill? All right, that fee starts January 1, 2024. Who gets the bill? That will drive what will be acceptable as evidence. How accurate do your emissions need to be? Your emissions measurements. Does it need to be just an engineering calculation, or does it have to be a measurement? And how much do you believe the measurement given the uncertainty bounds on what the measurements are? Right? Right now, the second part of that equation, the Inflation Reduction Act, imposes the fee. The fee is compared against what the reporting is for the greenhouse gas reporting program. And the greenhouse gas reporting program has instituted a new emission category called other large emission events. Right? So remember that Barnett animation that I showed you, all those increases, those super emitters? Those now get reported. And a key question will be, all right, maybe somebody flew over with an airplane and saw that emission event occurring. How long did it last? What's currently in the EPA proposal, how long you have to assume that it lasted, if you don't have any other data, is 182 days. All right, let me just give you the bill. What would be the bill that you get from the Inflation Reduction Act if somebody detected an emission event, single emission event at one of your facilities, and you didn't have any other data, and you had to assume lasted for 182 days? $1 million per event. $1 million per event for all those events, right? Who can detect these things? That's the third part. All right, that's in the new methane rule that should be final any day now. And in the new methane rule, anybody using a certified technology can identify an emission event on your facility. So Environmental Defense Fund is launching a satellite, methane sat, whose explicit purpose is to find these things. Carbon Mapper, another public sector entity, is flying over production basins. Recent study that they published identified 1,100 distinct, unique emission sources just in the Permian Basin over 2 months that were at this level. So who gets the bill is the question beginning January 1. And you better believe it's going to be litigated, right? And so what is evidentiary, and how do you trace that data is something that the United States, assuming all these proposals make it through to the final form in the EPA regulations, this is going to be on a really fast track in the United States.
So I think I'd just like to try to summarize what you said to make sure I understand. There are people out there, let's just say including yourselves and other companies, that feel like they can probably say who the emitter is on certain emissions, and they're going to claim that these emissions occurred perhaps when these fees occur, and then the companies may or may not dispute this, and EMMDL is trying to help, I don't know, trying to help solve this problem of people who claim there's emissions versus people who aren't.
Well, how do you even make it
Maybe
transparent? How do you
Yeah.
make a measurement transparent? What you get now from the 50 to 80 vendors that Arvin mentioned is they say, oh, pay us, we'll go make a measurement, and here's your number. All right. And no tracking, it's completely opaque. All right. And you compare these. So we've gone out and compared them. All right. And you're lucky if you get within a factor of 2 comparing between methods. Take them out and compare them to a controlled release. All right, either on a site or a simulated facility. Our team has done that too. You're doing great if you get it within a factor of 2. More typically might be a factor of 3 to 5. All right. So who gets the bill? What's the bill? And that will be played out over the next several years in the United States.
Right. Let me ask one more. It's related online, and we'll go to Michael.
Yeah.
Which is sort of what's the cost? You kind of played out maybe what the high end of the cost is. One of the questions online is how much do you think this will affect the cost of gas on like dollar per million BTU basis?
Yeah, I'll take a shot then.
Not kind of the stuff.
Well, so let's just use data from the International Energy Agency, all right, which looked at mitigation options. So how do you reduce it? The International Energy Agency estimated that out of the 100 million tons a year of oil and gas methane emissions, 50%, half, could be reduced, mitigated at 0 net cost. So the value of the gas at $4 gas that you keep in the pipeline pays for the mitigation once you've found it. Right, and that's the key, once you've found it. All right, and so there's still a search cost, right? But a lot of things we know where the emissions are, and so the emissions will go down for the known sources, but for these unknown sources, the search cost and how we drive that down is going to be important as well.
So, probably a lot of questions, we've been having time, but I mean, if an upstream company was to ask for your opinion, that if you get 50% reduction at zero cost, the costs are gonna start going up as the methane intensity goes down. I mean, from 4% to 3% to 2%, it's probably gonna escalate non-linearly. How would you guide a company that make the decision outside of any methane fee, to, on how they should go ahead and start looking at methane emissions? I mean, if you were to compare this to, say, social cost of carbon or whatever this metric is, if you were to compare that to, say, putting a capture unit on a combustion turbine, and understanding that there's a parasitical load on it, you have to actually generate 30% more gas in order to run the whole facility. How would you begin to come up with a suggestion on approach to that?
So I'll take a shot again. First thing to recognize is that we'll probably be able to answer that question a lot more precisely in another month or so when the US EPA's methane rule is finalized. Right now, of the known sources, so we have these unintended sources, produce super emitters, but of the known sources, what EPA proposed last November, it's expected any day to come out in final form, is something like a 87% reduction in known sources of methane from the oil and gas supply chain in the United States. So most of the routine stuff will be by regulation going away. So for example, pneumatic controllers. The proposal in November of last year was pneumatic controllers go to zero. You have to have zero emission controllers. You can no longer vent from controllers anymore in the United States. And so a lot of it will go away. And really it will become much more of an issue of these unintended emission sources. Right. And then it becomes, well, what's the incidence fraction on this? Just to sort of preview what we might tell people, if you look at some of the data that we have of some of these aircraft overflights, saying, all right, you fly over hundreds and hundreds and hundreds of these sites, hundreds of thousands we have data for. How frequently do you see in those snapshots one of these big emissions? National average, they're both from base, national average 1%. Right, so you're really looking for that 1% of the, at any given moment in time, 1% of your sites have these events. And knowing to what extent for your facilities it's recurring, versus it was a one-off and tomorrow it'll be at a different site, will influence what your sampling strategy would be. But more and more it's going to be going after the really big signals. So among the things that we're talking about with various operators are, can you establish, if you're looking for the really big ones, you don't have to have a very dense monitoring system to be looking all the time. So why not put together a coalition of operators that puts out a sparse network in production regions so that you can react like that? Yeah. Right? Making various presumptions, I think that's going to be a major direction going.
It'll be policy driven.
Oh, yeah, of course. And not just policy in the US, but policies around the world.
We have another question in the room. Go ahead.
Might be a follow-up question by thinking about this internationally. And, understanding that, not all places where natural gas is produced have a strip, will have a strip across the United States. Outside of agreements that come out of COPE next month, or harder pushes, like what incentives could you see that would get companies abroad to adapt the same standards, whether carrots or any other way to get them?
You just try to repeat louder online, this premise of the question.
Right, so the question is, how do you get other countries around the world to understand the importance of reducing emissions and get them to do some of these measurements and mitigation at the global level? Now, I think it's going to be a challenge. It's not going to be easy because the regulatory environment is very different around different parts of the world. But the key thing to see here is that what are the major buyers of natural gas want? So the major buyers right now are the European Union, Japan, China, and South Korea. And they're buying gas largely from 3 countries, Qatar, Australia, and the United States. There are, of course, other countries from North Africa that are going to expand production, but these are the major suppliers and major consumers. And you look at what incentives exist to reduce emissions on the supplier side, Australia, United States, and Qatar to some extent. They want to be global leaders in sort of low emissions natural gas. There's pressure from investors. There's regulations that help address emissions. But on the demand side, you look at what European Union policies are or what they're talking about. So right now, the EU is talking about a methane import standard so that they're going to give preferential market access to companies and countries that sell natural gas below a certain emissions level, or maybe a premium for price of natural gas if you demonstrate low emissions. Japan and South Korea recently launched something called the Clean Initiative to make sure that the natural gas that they're buying from buyers have low methane emissions. So the buyers are demanding this. And if your largest customer demands that you have low methane emissions, you're going to go do it, right? And so that's coming from the buyer side in terms of incentives to reduce emissions.
The thing I would add to that is that what's going to happen in 2024 is a vast expansion in satellite measurements that have global coverage at very fine resolution. So, it doesn't matter what your paper reports have been in the past. You're going to have eyes on your methane emissions globally, publicly reported. All right. And so you can say whatever you want about what your methane emissions are, but the buyers are going to look at the global reporting from measurements.
All right, there's another question online. It's kind of maybe just trying to clarify what you have here on the slide here about 2030. I guess the question is, what your goal is to complete the development of exactly what, or to continue how after 2030, or how do you view your role of the center and a date of 2030 and beyond?
You want to take that first?
I'm retired in 2030.
That's it.
So one of the key things is, the concept of MRE, measurement, reporting, and verification, has been in the news for a variety of reasons. If a company claims in 2040 that they have drawn down kind of 1 gigaton of CO2, you need someone to actually confirm that. Like, how do you trust that statement from a company? Or if someone says we have captured so much emissions and sequestered them under the ground for a period of 1,000 years, somebody has to monitor to make sure that the CO2 is not leaking out of the ground. There are different monitoring technologies to be able to do that, but the point is, as the total amount of CO2 we put into the atmosphere reduces, right now we are about 35 to 40 gigatons CO2 per year. As it comes down, the importance of measuring every molecule that's going to go into the atmosphere becomes much more important. Everyone's going to start counting, okay, how much am I contributing to the atmosphere? Because they're going to have a network, a web of policies around the world that will penalize you if you're emitting a lot of carbon dioxide and other greenhouse gases. So the concept of MRV is, I think, universal as long as we have carbon dioxide emissions. Right now, we're starting with natural gas because that's where we have most of the technologies and advances in policy, but we're going to need that very soon for blue hydrogen pathways. The tax credit in the Inflation Reduction Act alone is based on life cycle emissions of hydrogen production. I think the limit is 4 kilograms CO2e per kilogram hydrogen. How do you know that? And if you're producing blue hydrogen, if you're an operator that does capture at the end, you have to measure CO2 and methane across the entire blue hydrogen supply chain. So you're going to need MRV for hydrogen very soon. But soon after that, you're going to start thinking about MRV for carbon capture, for direct carbon removal, and for products that come in from other parts of the world. Right now, there is a bill in Congress called the Prove It Act, which has bipartisan support in both House and the Senate, that essentially says we are going to penalize other countries based on the carbon content of the products that they import. How are you going to verify that? And that's again going to require MRV across product supply chains, not just good supply chains.
All right, I'm gonna ask another question online, which somewhat related to this in life cycle metrics. I'm gonna ask the question directly and then I'm gonna add something. So the question directly is, GREET, the sort of life cycle model of argon, as are familiar with, well to gate emissions for natural gas as 13 grams of CO2 equivalent per megajoule. Is this reasonable or is it much higher? I'll just add my own question is, are we sort of getting rid of the usefulness of something like GREET if we have to go down to these very specific measurements of particular supply chains, of a particular company on a particular shipment? How do we even think about the use of tools like GREET anyway?
Correct. That's a great question because I think the quality of your numbers are directly proportional to the quality of the data that you put in. So GREET model is a great framework for thinking about wellhead to burner tip emissions. It was fine at the time it was created. That's the data they had, and therefore we had some uncertainty around the number. But now we have much better information on emissions across our supply chains. So we can still use the same framework, but what we have to do is make sure that the inputs that go into the GREET model reflect the latest measurements and information that we learn about emissions. So yes, GREET model is great. I love the framework, but we have to adapt it on a continuous basis to make sure that what the GREET model tells us reflects reality and not data from 2010.
So the GREET model uses as its primary information base for the United States what gets reported to the EPA. You compare all these measurements that have been made all over the United States on average to what's on average in the reporting in the US EPA, which is what is the default in the GREET model. You wind up with a number for methane, it's about 50%, 50% too low. And, so total for the United States is something like 1.2 to 1.3% over the entire supply chain instead of the 2%. So if I were to adjust the GREET model based on national level estimates for a national average, I would bump up the methane number by about 50% currently. Having said all that, though, one of the proposals on the table for the GHGRP going forward, again, that's what gets pumped into models like GREET, is now every facility is going to need to report, may need to report individually. It's still unclear where the EPA will go. But now there's the potential for having much more spatially resolved information in models like GREET going forward that rely on regulatory reporting.
So we could imagine perhaps every company or something like this just turns in their GREET spreadsheet with their reported numbers or something like that. Yeah, maybe.
Yeah, I think that the tension will be over the next 5 years that this reporting cycle and then integration into tools like GREET has something like a 2-year lag on it. And if we're going and reducing over the next several years methane emissions in the United States by 90% from known sources, the producers are going to want that information in there a lot more quickly than 2 years, right? So there's going to need to be a short-term way to address getting the most current information into those tools.
One more question. I know this is kind of like asking a watchmaker what time it is, but is this going to move the needle at all on the price of natural gas?
That's All right, let me answer it one way based on what you're seeing so far. Is it going to move the needle in the United States? Yes. Because this discussion about differentiated gas and more accurate information is just one part of several incentives that ask operators to reduce emissions. There's the EPA regulations. There is public scrutiny of emissions from oil and gas operators. There's investors that are demanding emissions reductions from the companies they invested. There's insurance companies that essentially go out and say, you need to reduce your methane emissions if you're going to insure you. So there are multiple drivers to reduce emissions, at least in the United States. So that's going to happen. Globally, it's a much more complicated picture because much of the oil and gas is produced by national oil and gas companies that are not subject to any investor pressure. But one of the things that we've seen happen just based on announcements is that there's a lot more LNG export capacity that's going to come online. Everything that's been announced does eventually come online. Then the demand for natural gas, if we trust some of the demand projections as well. So at some point, we are not going to be this very tight market where everyone's just going to need whatever gas is available, thinking of the last drop of natural gas. We'll move away from that in maybe 3 to 5 years. And then you'll come a time where you'll be able to see discrimination across the market. Well, there's a lot of gas available. Let me go find gas that has the lowest greenhouse gas emissions. I think we'll get there. That's my personal opinion, that we haven't done any modeling on this.
Yeah, and I interpreted your question slightly different way, so I'll answer it a slightly different way. If your question was, how much is it gonna cost?
Bingo.
All right, and what's the differential cost
Of all
to 1,000 standard cubic feet of gas? A couple cents, okay, to make the measurements. The much bigger effect is what Arvin was talking about. What's the relative demand for demonstrably cleaner gas going to be relative to a global average gas? And how does that compare to a couple of cents per MCF?
Thank you.
Okay, we'll do one more.
Like I really like the nature of transparency and the tools, and then like I just had a look at the methane emission estimation, for example. It's like publicly available, but it has not yet an open source license. So like, is there?
So I wrote my group wrote the MEET, the methane emission estimation tool, which allows you to do fine time scale resolution of measurements. And you can download that from a GitHub site and use it. The only restriction we place on it is we don't allow someone to put it into a product and sell the product. You can use it. If you have a company that needs that sort of tool, that company can use it. You can use it for business purposes, but we don't want people to take the tool, embed it into something else, and then sell that. If you want to do that, you have to come to UT and ask. But there are no restrictions on downloading the tool, using the tool for your own purposes. If you're having difficulty getting it, let me know and we'll get you overcoming whatever problem that is.
All right. Well, thank you very much, Dr. David Allen.